Welcome back, everyone. Today, I want to compute the Mandelbrot set, which is this beautiful shape right here. Now, I'm sure you've seen this shape, this fractal at some point or another, even if you're not really into maths or computer science, just because it's that well known. And the beautiful thing about this, or the very interesting thing about this fractal and the Mandelbrot set in general, is this property of self-similarity. So if we start to zoom into this shape, you will see the same patterns reappear in smaller and smaller versions of themselves. So right here we have these chambers reappearing, and if we zoom into right here, and I increase the number of iterations, the more we zoom in, we'll have to increase the iterations. We'll see the Mandelbrot set itself reappear, and even in this version, I can pick a spot, maybe say here, or there, and even in here, the shape itself will repeat. And in theory, this goes on forever and ever. Obviously, we're going to be somewhat limited with computation. Now, let's see if we can find one more. There it is. And just increase that. And you see, it takes longer and longer. So I have this beautiful illustrator by Ross Hill. And I'm going to be attempting to basically recreate something like that. Now, I don't think my version is going to be that advanced that I'll have zooming and iterations, at least for now. For now, I just want to get like a static image of the Mandelbrot set on the screen with Python, and then we can go on from there. Now, to just basically give you a vague idea of what it is, if you don't know the definition of the Mandelbrot set, it's this fractal on the complex plane. So what we're seeing here is the complex plane. So right here, along this axis, we would have the real numbers, and I don't know, maybe somewhere here, we have the imaginary axis, which gives us this 2D plane in the end. And if we pick some point C, some complex number C on this plane, how we test whether it's in the Mandelbrot set or not is by continuously applying this function, z squared plus c, starting with z equals 0, and see if it diverges. And if it doesn't diverge, if it stays bounded one way or another, then it's part of the set and we color it black in this case. We'll talk more about how to compute it in just a minute. For now, I do want to get the project set up. Now, I'll install the pillow library because, as I said, for now, I'm not going to be looking to make it interactable, to make zooms and stuff. So for now, a static image will be good enough for us. So then we can do from Python image library, import the image module. And with this, we can basically open, create, and to some extent modify images. And so what we can do is we'll call something like canvas. And we can do image.new, yeah. And then we specify a mode and a size, basically. So the mode is going to be, I guess, RGB. And the size of the image as a tuple, well, let's just make it 500 by 500 to just get something on screen. And this canvas, I can now save to a file. And let's just call it mandelbrot.png. And if I run this code, we should have a file in our directory. Yeah, there it is. And I'll just leave it open here so I can switch in between. And yeah, that's hopefully now a 500 by 500 image with a black background. We can change the color as a tuple. So for example, we can make it 255, 0 and 0, can make it red. Yeah, there you go, it updated. Or I think I'm just gonna leave it white though for now. Okay, and this is going to be our canvas that we're going to be trying to draw the Mandelbrot set onto. again, at least for now, I am maybe already thinking about making it interactable because it shouldn't be that difficult, but let's just get the basic logic set up. So, but I think instead of a square screen, let's do something like 900 by height, maybe 600. So we can just pass the width and the height in here. And yeah, I think that's a bit nicer to look at for us. Okay. Now onto the Mandelbrot set. Now, as I said, we're going to be dealing with complex numbers. No, let me just highlight that. Whatever. We're going to be dealing with complex numbers. And so we're going to need to implement them somehow into Python. Now, I know there is libraries for that or modules for that. I'm pretty sure NumPy has something, or I even did some basic research on arbitrary precision that we also have some complex numbers. But just for fun, I do want to try to kind of make our own complex number class. So complex number, because in Python we can very elegantly implement all the mathematical behavior and that stuff. So I think it's worth giving it a shot. So we'll do an init, and the complex number needs real and an imaginary part. So self.real is the real part. Maybe I'll call it imag is the imaginary part. And that's basically all a complex number is. And the rest are just the operations we're going to have with it. Maybe what I'll do, I don't know if we're going to need it, but I think it's going to be useful, is to have like a string method to be able to see the complex number. So it'll return an f string of self.real plus the imaginary part times the imaginary unit I. So we're not going to worry about the image for now. We're going to do the logic now. So in theory, I could call a complex number C, maybe 1 plus 3i. And if I print C, image, yeah, I already messed up. The imaginary part, no image. Yeah, there you go. We get 1 plus 3i. And I think that's going to be pretty useful for us to see it. Now, we're not going to need all the math operations for the Mandelbrot set, because all that we need is this function, z squared plus c. And I think this is a good time to actually maybe explain also how the Mandelbrot set works. So let me get up Paint. Maybe do something like this so I don't cover it with the camera. Yeah. We're going to start with some complex number c. So, for example, we can take our example of 1 plus 3i, and we're going to apply the function f of z onto that, more or less onto that number. So that is z squared plus c, and we're going to start with f of 0. So f of 0 is, well, let's just c, because 0 squared is 0 plus c is c. And now what we'll do is we're going to do f of 0. So, and that's going to be, well, now the argument z is f of 0, or c for us. So now we have c squared and again plus c. And I think you can see where this is going, because what we're going to do now is f of. So I'm going to use the colors to try to illustrate this iterative approach, f of 0. And now this argument z is this entire term. So now we're going to have or c squared plus c squared plus c, and so on. And this is gonna go, well, in theory, it goes on to infinity. We're gonna have some hard computational limit, but this is gonna go on. And basically, at every point, we're gonna check if it's, again, in theory, smaller than infinity, or some set value for us in computation. And if after some iterations, say, I don't know, maybe say 100, it doesn't diverge, is greater than some limit that we set, we can count it as part of the Mandelbrot set. And if it does, then it's gone. Then we don't care about it. Okay, so what are we gonna need for, what operation are we gonna need is, well, taking the number to a power, or I guess maybe a bit simpler for us, it's gonna be just multiplication. So let's think about multiplying two complex numbers. So we have some complex number a plus I times b times, maybe I'll zoom in a bit, times some other number c plus I times d. And we can just multiply out, so we get a times c plus a times d times I. And then we get this part, we get b times c, again, times I. And then we get b times d, and I times I squared. And as you probably know, for complex numbers, I squared is defined as -1. So we can simplify this a bit. So we get a times c, and I'll pull this one to the front. So we get minus b times d. And then this is the real part of our result. So the multiplication of two complex numbers, again, yields a complex number. And then we just have this part. So we get, I'll do a bracket, a times d plus b times c, and that is the imaginary part. Okay, so we can just implement this into Python, here into our complex numbers. We do def mul self, I think it's mul, because again, in Python, we can implement these operations with these with the dunder methods, self, and it'll ask for an other. Is it mul? I'm actually not sure, because I don't know why it's not showing up. Python dunder mul. Yeah, seems like it's mul. Yeah, okay. Well, let's just try it. We'll see. So, what we need is a is the real part of self. So we do turn self.real times c was the real part of the other number, so other.real plus actually, maybe let's wait a bit nice. We do real part is that plus, now we take the imaginary part of self times the imaginary part of other, self dot imag times other dot imag, and the imag part of the result, you can just look that up again, is the real part of self times the imaginary part of other, and then just swapped. So self.real times other.imag plus self.imag times other.real. And then we can just return the complex number of real part and the imaginary part. So let me just double check it and mess it up. A times c plus minus b times d, and then we get these mixed terms. Looks right. Okay, and now we should be able to have a number c1 and some number c2. That's just, I don't know, -4 plus 2i. So we can print c1, print c2, and then we can print c1 times c2. And let's see. I keep writing image. Why did I do that? here image. Okay, so yeah, there we have 1 plus 3i and minus 3 plus 2i, just as we've defined. And here we have the product. Now, I'm not going to double check it. I'm pretty sure that that works. Okay. And this should be pretty much all that we need. Actually, no, we need one more thing. Because how do we even define what the, how should I say, the magnitude or the length of a complex number is? Because here, remains bounded in absolute value. This is what we mean the number is smaller than infinity or doesn't diverge, is we look at the absolute value. And since we can think of complex numbers, let me just go over here. Since we can think of them as basically a vector on the complex plane, so this is the real axis, and this would be the imaginary axis. And then our complex number would be somewhere here. So I don't know, if we look at this number here, this would be 1 and this would be 3, or I guess 3i. To get the length, we just get the length that, like we do for any vector, so we just square the components and we take the square root. Now, square roots are computationally expensive. And in the most cases for stuff like this, actually unnecessary. So instead of doing the absolute value, we do abs squared, maybe, for self. Because let me just get this up. If we check whether 1 squared plus 3 squared and get the square root to get the length, Pythagorean theorem is smaller than some number, I don't know, n, or if we do just 1 squared plus 3 squared is smaller than n squared, doesn't make a difference, because right here I could just take the square root and I'd get the same result as before. So we don't actually need to, because we're going to be computing a lot of numbers, so all these square root computations are going to add up. So I think we can just use the square root, or the square of the absolute value to compare. So let's just define that as well. All right, so this will return, well, basically just self.real squared plus self.imag squared. And now I think this is all the computation, all the logic we're going to need for complex numbers. Okay, with this out of the way, let's get back to something more, to all the graphical stuff. Now, the way we're gonna represent the Mandelbrot set is by coloring the pixels on the image. And we can do that by, I think, canvas.putPixel, yes? And this will ask for an xy, the coordinate, where we want to put the pixel, and the value, which I think should be the color. Or maybe do we pass the color as a... Well, we'll see. We can just do a test. We can do at 100 and 100. And can I just pass as a keyboard argument? So I'll specify the color as red and we'll see if that works. I actually did not look that up. And it doesn't like it. Okay, maybe if I just leave it as the value. That looked good. Do we see it somewhere? 100 by 100 should be somewhere up here. Oh yeah, I think I... Actually, wait, let's try something like for I in range 100. Or maybe 10 for J in range 10. I and J, maybe let's try to draw a square with this. Oh, obviously, I saved the image before I actually do that. How about we move that down? And now it should work. Yeah, and now we get the square. Okay. Up in the top right corner, maybe we can do I plus 10 and j plus 10 to make it a bit more visible. So with this, we can draw squares. Okay, wonderful. Now, we're not going to be needing squares. Basically, what I'll do, again, for this first approach, for this first, maybe I'll make another part about this, is we'll just compute the color, I guess, or whether it's part of the Mandelbrot set or not, for each pixel on the screen, and basically the width and the height of my image is going to be the resolution of my Mandelbrot set. So we're not going to have any proper zooming like we have in this great visualizer, where it actually, like, if I zoom in quickly, see it recomputes the set as I pan and zoom. We're not going to have that for now. So, what we're going to need for that is we're going to need to loop over the entire image. So, you know, how about I put this into a function, so something like compute Mandelbrot of a given canvas. So like this, and then we can do just compute Mandelbrot of our canvas. And at the end of this function, we're going to save it. So what we'll do is for x in range canvas, and I think I can just access the width and the height for, I mean, I do define these global variables here, but let's just stick to this for y in range canvas dot height. And then let's try to just put just to fill the entire screen. Canvas dot put pixel on xy, and the color, or I guess the value it calls it, should be, I don't know, make it a dark green. So, okay. Yeah, and there we have the entire thing filled. Okay, how about maybe I do something like this? Let's just try x times y modulo 255, and we just do color. This should give us some interesting pattern. Oh yeah, that does look interesting. I mean, this is almost a fractal in and of itself. Like, looks kind of similar. Okay, I didn't expect that. But we're gonna use something like this to basically fill the screen. Now, what I want to do first, before we actually use all this complex number stuff that I did in the beginning, is we need to transform the coordinates. Because mathematically, or how the Mandelbrot set is defined, 0, 0 is, again, somewhere here. I'm actually not 100% sure, but basically, this is the 0, y equals 0 axis, and somewhere here would be the x equals 0 axis. Whereas for an image, let's make this white. Whereas for an image, I need to extend the screen a bit. The x and y are defined a bit differently. So their x and y are drawn like this, and this is the top left of the image. This is 0, 0. But we want to transform this into a mathematical coordinate system where x and y look like this. X and y. Yeah. So maybe to help visualize this a bit, what I'll do is draw some axes. draw coordinate grid. That's actually fine. So we'll do canvas.putPixel at the center of the screen. We'll do like a cross. So we do x, and the y coordinate is fixed at canvas.height over 2. And I'll just make this an integer just to be sure. And we'll do it, I don't know, let's do some gray, so 50, 50, 50 maybe. And if I compute that, what do you not like? No. Oh, x, and I need to close the parentheses here, like this. Yeah, and then we have the x-axis, and then we just do the y-axis. So that's going to be at x equals the integer part of canvas.width over 2 and some y value. Okay, let's run this. And here we have the grid. So right now 0, 0 is up here, but I want 0, 0 to be down here. So for example, if I do canvas.putPixel at 0, 0, and let's make it red, you will see, yeah, you can barely see it. I'll try to zoom in a bit. Yeah, I don't know what YouTube compression is going to do to it, but yeah, you can see the pixels up here where we would expect it to be down here. So we need to transform the coordinates a bit. And what I'll define for that is a function called map, maybe that's map range, where we're gonna map some x, some value x that comes from the interval x min, x max. We're gonna map this to some target interval, so target min and target max, I guess. Will we? Yeah, because yeah, I think it's better if we already do it like this. Because right now also is what some worry is. If we just use x and y, they start at 0 and go up to 900 and 600, whereas the Mandelbrot set, what we're seeing right here is, again, I don't know if I can like visualize it, or we can see it somewhere on Wikipedia here. Yeah, right here. Yeah, there you go. Look, it's bounded somewhere between like 1 and -2 and I and -I. So if we just naively just compute it for this x and y coordinate, the Mandelbrot set would be limited to just this top left corner, or like the center, I guess, even if we remap it, so it would be really small. So we need to renormalize this interval from 0 to 500 to say -2 to 2. So this is, I think, a bit smarter if we already do it like this, because there we can also change basically the origin. Okay, if this didn't make too much sense, just bear with me for a minute. Let's just try to get this map range. Then we map some x coming from some target interval, or from starting interval to some target interval. So what we'll do is, let's call it, I don't know, length, I guess, is x max minus x min. And basically what we want to figure out first is how far along this interval we are. So percentage is x over, maybe let's just call it interval, over the interval. And now what we need to do is just, because that's going to be some number between 0 and 1. And now we just need to lerp this to the target interval. So do linear interpolate. So target x is going to be, and the lerp, the way I always remember it, is we do plus the value at 0. So if this percentage is 0, what do we want the value to be? And if it's 0, so if it's x min, wait, is this even the right thing? X over the interval. Well, whatever. We'll double check this in a second. It should be the target minimum. And if it's 1, so if we do percentage, what do we multiply the percentage with if it's 1? Well, if this is 1, I want the target max, and I don't want, so I do the minus, the target min. So it should remove the target min if the percentage is 1. Yeah. You know, let me just double check if I've done this correctly, because I'm a bit unsure just for the moment. So we do maybe map range or print. Actually, I can do printing this. So we just do map range. X, say I don't know, 1. And it comes from the range 0 to 10. So it should be 10%. And, okay, whatever. Target range should be, I don't know, say 0 to 100. And in here, I'm just gonna print the percentage just real quick. Yeah, 0.1. Yeah, that looks about right. So if I do maybe 2, we should get 0.2, so 20%. Yeah, okay, I've done this correctly. And what if we start from 10 going to 20, and I'm at 10, I should get 0%. Yes, yeah, that actually doesn't work. Of course, I need to input the offset. So we need to offset it by x minus x min. We should do. And now I get 0. And if I do maybe 15%, that should be half, so 0.5. Yeah. See, I knew there was something off. I'm sure you were screaming at me already. I need to offset it to get the percentage. Okay. And now I could return, for now, let's just print the target x. So I'm mapping basically, I'm at the half point of my starting interval. And now I should get the half point of my target, and also, in this case, 50. And I do. And what if I change the interval from 100 to maybe 300? So the half point should be 200 now. Yeah, that looks about right. And the good thing about the lerp is I can actually invert this. So if I say I want to map it, an x coming from 10 to 20, I want to map it to 300 going from 300 going to 100. Well, okay, I guess it doesn't make much difference for the half point, but let's just do 19. So I'm almost at 20 mark. So I'm at 90%, and now it maps it to 120 because I've changed the order here. That's the good thing about the lerp, and we're actually gonna need that. Okay, also one thing, so instead of printing, we'll return it. Also, what I want to do is ensure x is in start interval. I just got a message on my phone, but we're gonna ignore that. And so what we'll do is say x should be the maximum between x and x min. So if x is smaller than x min, the maximum will raise it back up to x min. And whatever that value is, we'll want to take the minimum of that value and the x max. So again, if whatever we've input is larger than our maximum, we'll want to bring it back down. So with this, I should be able to input, I don't know, say 25, and this should be interpreted as 100% just. Oh, wait, actually, I need to print it now. Print. And yeah, there we get 100%. Whereas without that, if I comment this out real quick, this will overloop and now, okay, in this case it goes down to 0. But we don't, I mean, I don't think we're going to run into that issue because we're going to be limited to the screen width anyway. But, you know, it's nice to have in there to avoid some unexpected behavior. Okay, so now what I can do, you know, let's call this I and J, because these aren't our real X and, I guess, Y coordinates of our coordinate system, but instead there are these arbitrary, like, image pixels. We'll do X is map range of this index I. That is coming from 0 to canvas.width. And I want to map it now to, say, -2, 2. And we can do the same thing for the Y. No? Map range. And that is J coming from 0 to canvas.height. And I want to map this to, again, say -2, 2. Okay, and now I should be able to just draw, maybe do canvas, actually I can just keep that at, let's try to draw it at 0, 0. So if x equals 0 and y equals 0, so I need this if statement because I'm looping over everything and I don't want to remove the loop. So at x and y, no, but I still want to draw it at I and j. So basically, x and y are what I use mathematically, and I determine, okay, it's 0 and then 0, but I still draw it at I and j. So if I didn't mess up anything, yeah, the pixels in the sentence, I removed the, did I remove the act? Oh, wow. Okay, then maybe let's actually keep it in the for loop. We can just use one. Actually, let's not use one loop because then it gets like overridden and stuff. So I don't want that. So we just do something like this. So we do canvas.put pixel at I and canvas.height over 2, integer value of that, and we do 50-50. I'm basically just redoing what I've done before. And yeah, that's right. We do at int of canvas.width over 2 and j. Okay, so now I should get the grid back. Yeah, and if I zoom in, you can see the center 0, 0 is now red. Okay, wonderful. Now, let's try something else. How about we do the colors now depending on the x and y, the x and y value. So we put the pixel at I and j again, and now the color should be, I'll define it right here, I think, should be, let's do x times y. What do we get there? You know, I did want to play around with it a bit to just see if the logic works. Yeah, I'll need to make it an integer. Wait, can I not just do int x times y and then do times 3? Int. Oh, actually, wait. If it also accepts an int, can I just do this? Is it then just grayscale? That's an interesting result. Oh, because, well, what if I do times 100? Okay. That's an interesting result. Okay, whatever, then just do like this, int x times y, and have it 3 times. I'm actually not sure what the value is. Is it just basically hexadecimal? I mean, we can look it up. Wait, let me look it up. I'm interested now. Python image module put pixel. What is the value? Value, a pixel value. Is it just a hexadecimal number? If it's an integer? Let me just try that. So what if instead of this we do 0x ff. This should give us white. And now maybe do red. So ff0000. Or is it RGBA? So we do 00. No, we do ff. Yeah, okay, so it's basically just RGBA as a hexadecimal number as the value. Okay, I see. That's interesting. So, for example, if I do the green... Actually, why is this purple? Oh, is it a RGB? Oh, wait, so it's a RGB. So this is the... Oh, yeah, so... Okay, so this is the alpha. So I want full opacity. I want red color. 0000. Okay, this is blue now. Okay. I know this is not the subject of the video, but I'm genuinely interested now in what that value is, because it definitely looks like some hexadecimal stuff. The pixel value. But actually no, the mode should be set to RGB, not but there's a RGB, not RGBA. So actually, so this should be green. Okay, okay, wait, then what did I mess up before? So this is green, then this is blue. No, this is red. Oh, is it just inverted? So is it like this is R, this is G, and this is B? So that's blue. Oh, seems like it. Okay, so mystery solved. It's just some backwards RGB. Interesting, I've never seen that before. Yeah, wait, so let's go back to color. That's still black. Times 100. Oh, I mean, actually, wait, I need to like, wait, hold up. I need, instead of 100 or times 100, I should do like a mod 255. Still? Well, what is the color? Oh, no, that's not what I wanted. What if I do times 100 in here? Yeah, no, actually, I can. Okay, it's gonna take a second now because it's printing all that stuff. Yeah, okay, you know, stop that. It's not printed. Yeah, okay, this is more what I wanted. Okay, so now we see that along the x and y equals 0, we get black because x times 0 even times 100. If it's 0, then 0. And right here we get these white values, and every now and then when it hits 255, it just goes back to black. Okay, so that looks about right. Okay, wonderful. So, okay. Basically, what we're gonna do now, I know this was a bit of a detour, but whatever. We're gonna kind of cast this into a complex number. So the x should be the real part, and y should be the imaginary part of that complex number. And now I just need to compute the Mandelbrot, and I'm just realizing maybe I should call it compute, maybe draw Mandelbrot. Draw Mandelbrot? Because I'm drawing it, I want to compute it somewhere else. So I'll do def compute Mandelbrot of a complex number C, and we can maybe also type hinted right here. Okay. And now here comes the part we talked about, where we iteratively or continuously apply this function f of z, starting with z equals 0. So, what we'll do is for underscore in range, say, let's just do 100, or let's just do 10 for now, to just see if it works. And I'll call z equals complex number 0. Oops. 0, 0. Actually, we can maybe also just at initialization, we can just do it that by default it's 0. So then I don't have to type anything in here. For the complex number 0, 0, we're gonna compute z next, because basically that's what it is to apply the function one time, so we get the next z. So by applying the green function here, I get the z value for the next iteration. So z next equals z times z plus c. And I mean, I guess I might as well already just call z, because yeah, z next is the next z, and then for the next. Okay, let's see how that looks. So maybe I can even do it up here. Print. Let's print the z to see it in action. Print z. We'll do compute Mandelbrot of the complex number 1, 1. Let's see how that works. Oh, okay. Yeah, look, I actually even forgot something. We need to do the add. Yeah. Yeah, so we did the multiply. We also need to do the add. So def, again with the dunder method, add self and other. Well, how do we add two complex numbers? We just add the real parts and the imaginary parts. I don't think we even need to go into paint for that. So we do real part is self.real plus other.real, and imag part is self.imag plus other.imag. And then we just return the complex number, real part, and imag part. Okay, now it should work. Oh boy. Yeah, I mean, I think you kind of see what's happening here. So we get 1 plus 1i, 3 plus 3i, 90 plus 19i, and then it kind of explodes right here. So it maybe, to see it a bit better, print. We just do print like an empty line right here. Okay, and it's complaining that I haven't defined color. Here, can I? No, that's not what I wanted. Okay, I still haven't set up all the short the keybinds on this setup right here, but I mean, as you can see, the numbers get larger and larger, and compute Mandelbrot. So if we look at the Mandelbrot set, we've just computed the first 10 iterations, and I think, if I haven't messed up, it's safe to say that this number diverges pretty quickly. Actually, we can even print the length of z, dot abs squared. We could print that instead. Yeah, okay, and then it's complaining that the color is not defined, whatever. So it has had length 2, then 18, 722. So again, it's safe to say it's diverging. So if I look at the Mandelbrot set on Wikipedia, and we look at the axes are a bit different. So like this is x equals or like 1 and y equals 1i. And as we see, it's indeed not in the Mandelbrot set. It's not colored really here, but these bright areas are part of the Mandelbrot set, and this one diverged, even after 10 iterations. So let's try. What happens if we do, let's not do 0, 0. Let's do here. Minus 1, 0 is in the set. Let's do minus 1, 0. So for minus 1 and 0, we should see it bounded. Yeah, so yeah, I'm just going to fix this real quick because it's actually annoying me to do whatever, just do red. You see the length oscillates between 1 and 0, so no matter how long we'll go on with these iterations, it's going to be 1 or 0, which is obviously much less than infinity. So it's part of the set, even after 10 iterations, even with this very, very simple and rude and crude like computation, we can already see some numbers. Okay, now what I'll do in here is do something max iterations. So instead of 10, we have, say, 100 iterations. Max iterations. And then, after each, I computed the next z, I should check if it's bigger than some arbitrary value. And we'll call this an escape radius. And I'm pretty sure I read on Wikipedia that an escape radius of 2 is usually taken for the Mandelbrot set, which is enough. So because I guess apparently if it's larger than 2, it's gonna diverge anyway. I haven't like double checked this, but we'll see if it works, I guess, because we'll either see the set or not. So after we've computed the next z, we do if z.abs squared is larger than escape radius, and again, because I'm dealing with the square right here, we'll also have to square the radius, that and yeah, basically what this is going to return is going to be a true or false. So again, guess I can type it to a bool. So it's going to return true if it's part of the Mandelbrot set. Actually, again, I don't know what's going on with my naming today, but compute let's rename this as well. Let's call it part of Mandelbrot, I guess. I don't know, I'm not that good with naming today. I don't know why. If it's starting to diverge, we'll return false. And if we've made it through these 100 iterations, or however many we're going to set, and we never reach this radius because we've always been 1 or 0, for example, something like that. If we've reached this, we'll return true. Now, again, this is a bit of this is the limit we have with computation. we're never going to check infinite iterations of this, because it could be that some numbers, I wouldn't know any off the top of my head, that for some C it's starting to diverge really slowly, that even after 100 iterations it's below 2, the length is below 2, but after, say, 200 iterations it'll start to diverge. We're not gonna catch that, so we're gonna have some error. And this is why in here, the further I zoom in, so we need to increase the iterations, because at some point you'll see some artifacts like this. And I'll zoom out a bit, and if I increase the iterations here to 12,000 iterations, you'll see the detail again of these shapes that we just didn't see with 800 iterations, because it just fails to capture that, because, okay, well, it says these numbers diverge and these black ones don't. So this is the limitations we're gonna have. Okay, but that's fine. So we have we can check if one number is part of the Mandelbrot set, and so we can do that. So right here, we can do if, actually, no, we'll keep the complex number. If part of Mandelbrot, if C is part of the Mandelbrot set, then the color should be, let's do black. So, I mean, I might as well define these as well. So we can do black is 0, 0, 0, and white is 255, 255, 255. So if it's part of the Mandelbrot set, we'll color it black. Actually, let's do white, whatever. Else, if it's not, we color it black. And so okay, let me just break down again what we're doing. So we check I and J, we check every pixel in our image here. We go around, check every pixel. We convert that pixel to some x and y that we've arbitrarily mapped to -2 and 2 for now. We check if that xy interpreted as a complex number is part of the Mandelbrot set. If it is, we call it white. If it's not, we call it black. And yeah, wait, here I need to set the color. All right, let's see. Yeah, okay, wait, I need to call the method here. Okay, no error message, and moment of truth. That does not look like the Mandelbrot set. Like, at all. Okay, interesting. I mean, it shouldn't... Is it an issue with the iterations? No, it shouldn't be. No, okay. Is it with this escape rate? Okay, what if I set it to 1,000? Yeah, okay, that's fine. Let me just clear the terminal. So, okay, no error message. Okay, it's not part with the... No issue with the escape radius. Okay, what did I mess up then? I mean, it is not diverging because, yeah, it stays pretty bounded here, yeah. But it should diverge, I guess. You know what? What I'll do, you know, I'll compare my results with GeoGebra here. And then we can see if my loop is wrong. So we do Z equals what do we say? Minus 1.75 times 0.2 times I. Times. Wait, I need to add a plus here. It's about to say that looks wrong. Yeah. And now we do, and we can define like f of c, we do, oh no, for z is z squared plus, and we'll call this c plus c. And now I can just do f. So f of 0, I get that, which we get here as well. f of 0. Let's see, there we already have some difference, because here I get 1.27 and I get 1.35. So did I mess up the real? Oh wait, you know what? Oh. Oh boy. What did we say? A times C minus B times D. What did I write? Real plus the... well. Okay, again, I don't know how much of this you guys saw, but this, I don't know, this took me way too long to find. And I even double checked this like twice. I do remember, so... Okay, we found it. Okay. Pretend like this didn't happen. We do... I'm gonna leave the escape radius high, just for a second. Okay? We can get all this back. Nope. Nope. That's all that here. Get all this back. We don't need you, and I'm gonna move you up here. Indent you. We put the pixel at I and J. And we make the pixel the color that the Mandelbrot set decides. Please just work now. Okay. Oh. Okay. That's good. That's good. We have the Mandelbrot. It looks squished, but that is because I have some weird aspect ratios. Maybe we should return to square aspect ratio. So there we are. Oh, beautiful. We made it. We've done it. Also, one thing that I kind of realized midway through is, I mean, it doesn't actually matter for the Mandelbrot set, but the y needs to be flipped. Because, as we can see here, for the image, the y points down, but mathematically the y should point up. So technically, I would need to do it from 2 to -2. But since the Mandelbrot set is symmetric, we don't really care about that. But this was just a small thing I realized. Okay, you know what? How about... And wait, I'm curious about this escape radius, because I was really skeptical about the 2. If that's enough, because like that's still really far from infinity. But no, it doesn't look much worse than with 2,000 or whatever that was. 20,000. No, just run the file. There you go. Let's see that. Yeah, I don't think anything changed. So yeah, we can just stick to 2. So just quickly, almost an editor's note. In the video, I was wondering why you choose an escape radius of 2 and whether that's big enough or we're gonna run into some issues. The short answer is no, there are no issues, and yes, it's big enough. Basically, you can think of it like this. So if the point that if our function at any point grows larger than this radius, it would be the same as if we would evaluate the Mandelbrot set, or whether the point is the Mandelbrot set for some point outside this circle, like for example this one. And as we can obviously see, if we just sketch it out real quick, I just took the image from Wikipedia. If we sketch it out real quick, we can see that the Mandelbrot set is contained within this circle of radius exactly 2, and here this tail is the last thing that sticks out, or like that touches the edge of the circle. So the escape radius of 2 is exactly right, because that's the smallest radius that still contains the whole set. But yeah, back to the video. Okay. How about, I mean, I know it's gonna take a while to compute. How about I do a giant image, 9,000 by 9,000, and I'll let it compute. Okay, so it's done now. It actually took, I don't know, like 10 minutes almost. I went ahead and made myself a cup of tea and well waited. So yeah, here we have the big Mandelbrot set. And we can indeed zoom in, and we see more and more of these patterns, but also what we can see is these artifacts really quick. So we would need to crank up the number of iterations. Now, also, I don't know if I'm imagining this, but if I compare it to like the proper visualization, I do kind of feel like my Mandelbrot, like my version, oh, there it is a bit squished, isn't it? If I compare this, which I mean, actually, wait, I know why, because now the aspect ratio is uneven again. So, you know what? How about we just keep it at -2 to 2 to just have a proper aspect ratio. I'm gonna reduce the size. Yeah, let's just have 500 by 500, because this code is inefficient as is. So like there's no use in trying to get something out of it, because it's gonna take an insane amount of time. So if I run this again now, it should be a bit faster. But yeah, there we have the Mandelbrot set, and okay, that looks fine. Looks a bit crappy because we only have 100 iterations. But what I want to do, I know this is going to be a long video again, but what I still want to do is to color it properly. Because, I mean, yeah, that's what there is. That's fine, it's the Mandelbrot set, and if we wait long enough, we get an arbitrary precision base, or more or less. There are limits, but, well, what I want is now to have some color scheme. And how they work is basically that they show how quick it diverges. So I'll remove the type hint here, because we're going to change this from a Boolean value to I guess a tuple. I guess some integer. So we can leave the type in it, but just make it an int. And we'll basically track a time. Oh, okay, whatever. We'll basically track a time which it takes for it to diverge. So if we diverge somewhere in these iterations, we'll return this time t. Let's do over max iterations, I guess. Yeah. So it's some gotta be some number between 0 and 1. And if if we don't hit the thing, we're gonna return I guess 1 as the value. Yeah. Yeah, okay, I think that works. Okay, so basically if it diverges after like the first few iterations, we're gonna get some really small number. If it makes it all the way through, we get 1. And now we can use this to color it. So we call this escape time is okay, I guess we'll leave the part of Mandelbrot, whatever. So is C. And now we have this escape time. And now I want to map it to basically a color. So we can do color is we could reuse the map range function. We'll map escape time coming from 0 to 1. Okay, sorry, I keep on getting interrupted today. I don't know why, but anyway, so I'll try to be quick about it. I know this video is long. So we're coming from 0 to 1, and we'll map this to basically some color. And I'll just try maybe 255, 0. And see how that looks. So actually, no, the color should be is some tuple. And that should be no red, no green, and the blue channel should be done by this. Let's see how that looks. Float object can be interpreted. Yeah, okay, obviously we make this an integer value. Okay. I mean, you can see some color in there. Some slight. Again, I don't know if the YouTube compression will do it any justice, but that's not necessarily the result that I wanted. Okay, how about we just rescale this T? How are we gonna go about this? I haven't really looked it up how to get these nice colors. I'll try. I was kind of hoping we could. I'll figure it out on the fly. But if not, I'll have to do another cut and I'll get back to you. But well, let's see. So how about I just return T if it was in some if it diverged at some point, and if it didn't, let's return -1. So so if escape time is less than 0, so if it's -1, we'll do color is black. I actually have it defined, so black. Else, color is just gonna be and how about we just map the escape time from... How about if I just flip this? I don't think it's gonna make much of a difference, but we'll see. So, okay, that's more what I wanted. So now we again, the resolution's now a bit low, but we'll have to deal with it. Now you see more of this. And how about if I rescale? If I say it's not max iterations, but it's, what is the max iteration? 100. What if I say it's 50? Let's see. Yeah, there you go. That's more the look I wanted. Let's actually also go down to maybe 25. Yeah, there you go. This is what I was looking for. That looks good. Actually, also what we could do maybe is, what about we give it some... We don't make it black if it's diverging. We give it some color. Oh, and now it has like a halo. Look at that. Get make it 20. Yeah, I like this. I like this. Okay. What I'll do, I think, is I'll export some higher quality image of this, and and yeah. Okay, so that took another like 10 minutes to compute, and I'll be honest, the quality is not that much higher. We'll have to do something about the resolution, really, of the iterations. But you know, for now, I'm really happy actually with this result. I think it looks really good with this halo effect, this glow effect. Now, I think I'll call it here, part 1. I've been recording for almost 2 hours. I don't know how long the video is gonna be, but that was enough work in and of itself. What I'll do is I will make a part 2 where I'll try to implement the zooming that will open it in some interactive window, and we'll be able to zoom in and dynamically change the number of iterations, and there I'll also think about some optimizations with NumPy, or we'll see what I come up with. But yeah, I think we can leave it here for now. Thank you very much for watching, and I'll see you in part 2.